On the 26th of April 1986, a huge disaster took place at the nuclear power station of Chernobyl, currently located in the Ukraine. Previously, at that time, it was in the Soviet Union. A nuclear reactor exploded. A whole reactor exploded. 43 people were killed outright during the disaster, but it is estimated that another 4,000 to 20,000 will die because of it, and the number of the death toll has already increased quite a lot above that 43 by now. But how is it possible? How can radiation kill that many people? What does it do to your body? And how much do you need to get? Well, that's what we're going to see in this video. We're talking about radiation hygiene. Radioactive radiation is unavoidable. It's everywhere around you. You can't avoid it. And the dose of unavoidable radioactive radiation is called the background radiation. So the background radiation is dangerous for you? Yes. Can you avoid it? No. Just accept it. Only radiation, radioactive radiation, to better put it, ionizing radiation, because there's also this type of radiation that does not come from radioactive radiation, like X-ray photos. Only the otherwise received dose can be minimized. And everything about how do you receive that dose? What does it do to your body? What kind of precautions can you take? How do you measure it? Everything around that is called radiation hygiene. And that's what we discuss in this video. First of all, that background radiation. What does it consist of? Well, what are the sources of the background radiation is then quite important to know. First of all, cosmic radiation. That's the main source of background radiation all across the Earth. That's because we are in this universe, and in this universe there are stars, and stars send out radiation, ionizing radiation, because of the nuclear reactions taking place inside those stars. And that's coming from everywhere towards us. So, avoidable? No, definitely not. You can hardly switch off the stars. It would be not very good for us. Natural radioactivity. You'll find radioactive sources all around you, radioactive materials. First of all, there's in your food. Hydrogen-3 is one source of radioactivity. Carbon-14 and potassium-40, those are radioactive isotopes that occur naturally in your food. And we can't take them out. So just accept that they're there. Ground which you walk on. There's all kinds of radioactive isotopes spread around the ground. And we use the ground for building materials. So there's thorium in your walls if you're living in a house made of concrete or stone. Can we take it out? No, we can't. So avoiding this kind of background radiation, there's 4 things you need to do to avoid the risk of this. Stop eating, stop drinking, stop breathing, and move to another universe. The first 3 will have possibly some quite negative effects on your health, which are stronger than the results of the radioactivity. And there are some practical difficulties with the latter one. Probably the post will have some trouble forwarding your mail, I think. So these you cannot avoid. And alas, the last source you cannot avoid either, but that should have been. That's called fallout. And that's background radiation caused by humans. Yeah, we're not happy about this. Should be a little bit, very much ashamed of this. Like Hiroshima and Nagasaki. The nuclear bombs thrown on these 2 Japanese cities at the end of World War II. But the radioactive material was spread around the whole world through the atmosphere and still measurable here. No good. And the years after that, nuclear powers around the world continued to test nuclear bombs above ground. The radioactive material, those is also spread around the world and can still be measured here as well. And there's the grave nuclear accidents, which also made sure that caused nuclear radioactive materials to be spread around in the atmosphere. The four biggest ones were Windscale in 1957, England, Harrisburg in Pennsylvania in 1979, Chernobyl, which you already mentioned, in 1986, and the most recent one in Japan after the earthquake, Fukushima, where multiple nuclear reactors actually blew up and spread the material. Yep, that's all things that should be avoided. Well, if everything around us is radioactive, then what do we call a radioactive source and what won't? Because radioactive material, that should be disposed of in a special way. If everything around us, what do we call radioactive waste and what not? Because of that, there was we've decided to call something waste limit. That's a limit. It was chosen. It's not actually something given in by physics, but it's just a matter of being everyone saying that is it. There is the limit. That's 100 becquerel per grams. So if you are above the waste limit, that's a radioactive source, and you have to take all precautionary measures, like having it transported by a special service. And if you're below it, well, just dump it in the dustbin and throw it on the waste mount. Is that an easy to reach limit, the waste limit at 100 becquerel per gram? Well, if you're not doing anything which we call radioactive sources, no, you won't reach it. The most radioactive object you can come across in your daily life, which is not deliberately made radioactive, it's a banana. And that's still about 1,000 times below the waste limit, so you shouldn't need to worry about that. How do you receive radioactive radiation? Where does it come? How does it reach your body? There are three mechanisms by which you receive radioactive radiation. The first is irradiation by an external source. The radioactive source is quite a distance away from you, and it radiates its radiation towards you, at least part of it. And only that part you will receive. Most of it will not go in your direction, so you will not receive it. There's what we call surface contamination. Then the radioactive source is on the outside of the skin of your body. And since radioactive sources radiate their radiation in every direction, you will receive half the radiation in your direction towards your body. So that's already more severe than irradiation by an external source. But what can be even worse than surface contamination? If you get 100% of the radiation towards your body, and how then can that be? If it's inside, internal contamination. How do you reach internal contamination? How do you get a radioactive source inside your body? Well, medical treatment. If you're treated for cancer, for instance, they put a radioactive source inside the tumor, and then, well, yes, the patient becomes a radioactive source. That's true. Accidents, like the ones we mentioned, in Chernobyl, in Fukushima. You breathe, or the food is contaminated by lots of radioactive materials. It was also here, after the Chernobyl accidents, there was so much radioactive material came free into the atmosphere and rained down on the plants that people were not to eat allowed the food they grew in their own gardens, because it was above the waste limit. If you had eaten it, You had internal contamination because of that accident. Carelessness. If you work professionally with radioactive sources and it becomes routine, well, when things become routine, you start making mistakes. And that can cause you to get radioactive material inside. You forget to wash your hands and have your lunch afterwards, for instance. And then there's one you might not think about, but that really is also internal contamination. Smoking. Really bad for your health. Also, not only because of radioactivity, but that's also something which really contributes to the dangers of smoking. Remember, polonium-210, that's the stuff contained in tobacco smoke, and that's a source of alpha radiation. And remember that it's alpha radiation inside your lungs. We'll get to that in a while. Now, what does radiation do to your body? Well, what are the effects of radioactive radiation? First of all, there are the direct effects. And what is the direct effect of radiation? Cell death. Your cell is too damaged to continue working. And yeah, well, it just stops there. It just sits there in your body until it's broken down. It will not divide into new cells. It just stopped there. But you consist of 2 billion, no, actually 2 trillion cells. What do you notice if one cell is died because of radiation? Well, not much. This is only, you've noticed something about this when many cells are affected simultaneously. Well, simultaneously is not that literally like in a fraction of a second, but if you get that in a couple of hours or a day, that's still killed simultaneously. Your body just doesn't have the time to restore those cells before the effects are noticeable. And what are the effects of the direct effects of radiation? Well, the first of is a red skin. Ooh. Have you had a red skin after you've been too long in the sun? Yep, that's radiation damage to your skin. Just one little thing that's fortunate about that, it's caused by UV radiation, ultraviolet, and that doesn't go any deeper than your skin. So your skin is damaged by the radiation, but not the rest of your body beneath it. So if you know you got a red skin because of X-rays or gamma radiation or alpha or beta, you know that there's quite a lot of things happening below the skin as well. But still a red skin because of UV, that's still quite a cause of skin cancer. So it's not good either. Initial radiation sickness, that's the next level of direct effects. That gives you extreme itches. Think about that itch at a little spot on your back which you can't reach. Yeah, can you imagine that? Now think that is happening all through your body, also on the inside. That's initial radiation sickness, and that's only the things you're feeling from it, not what is happening more. So not good. But even worse is the next stage, that is severe radiation sickness. Whole organs stop functioning, and the first of all is your bowels. They stop functioning. Not good. Still, you have a more than 50% chance of getting through that, of surviving that. But it must be mentioned that if you survive this, it will have lasting and permanent effects inside your body, which you will always have to take care of. But then there's the fourth stage of direct effects. There is so many cells that are died because of the radiation that your body cannot recover from it, and then you die. Yeah, but only this is the effects if you have very many cells affected simultaneously by very high doses of radiation. And that's not actually happening very quickly. You really have to do very, very strange things for that. But what about the daily life? That's more the indirect effects. the cell is mutated. Well, that's not actually the result of the radiation itself. The radiation damages molecules inside your cells, like the longest molecule you have, DNA. And there's a mechanism in your body that if your DNA is damaged, it tries to repair it. But there's a little bit of a snag on that, because the DNA is like a sort of jigsaw puzzle of which the pieces will fit together in every kind of way. So if the jigsaw puzzle is laid but in a wrong way, yeah, that cell is damaged, and the result, the code in your DNA is changed. So the cell will be working differently, and that can be either in a positive way, but also in a negative way. And if the mutation is in the division mechanism of the cell, that's the result is cancer. So that is indirect effects. And that can be dangerous, and that can be noticeable many years later. So therefore it is important to measure how much damage is the radiation doing to your body. How can we estimate radiation damage? Well, very roughly, if we use the activity of the source in becquerel. That's saying only something about the emitted radiation and not about the received radiation. So that is a very rough estimate and absolutely nothing to measure it. Only usable if you get absolutely nothing better. But this is just a very rough estimate. And it doesn't take into account other things that are also important. So we may conclude activity is not a valid quantity for measuring the radiation damage. And we're going to do 3 more steps that will lead us to the quantity that is used for measuring the radiation damage. First of all, the dose, symbol D, and that is the absorbed amount of radiation energy per kilogram of body mass. The D, the dose, is the radiation energy divided by the mass. And the unit of measurement is the gray, is the joule per kilogram. Still, this is an estimate, because amongst other things, it doesn't take into account the type of radiation which you absorbed, which is also important to know how much damage it does, because your body can recover easier when it's damaged by the one sort of radiation than by the other. A more accurate way to measure the radiation damage, the equivalent dose. That's some kind of new formula. D, by the way, is the dose from the previous page. E is the equivalent dose. What does WR mean? Oh, by the way, the measurement of unit is the sievert. WR is the radiation type weight coefficient. So how much more dangerous to your body is the one type of radiation compared to the other? Well, here is a list of the naturally occurring types of radiation. Alpha and X-rays and gammas all have a radiation weight coefficient of 1. So if you receive 1 gray dose of beta radiation, that's also 1 sievert of equivalent dose. But if you get 1 gray of alpha radiation dose, your body can recover quite more difficult from that, because the damage is contained in a very limited area, and that's harder for your body to recover. So 1 gray of alpha radiation means 20 sievert of equivalent dose. Now think a couple of pages back, what type of radiation was coming from tobacco smoke? Alpha. Time for alert? Yes, time for alert, but not yet complete. Because there's something more that we should take into account, and that is what tissue in your body is absorbing the radiation. That's also worth noting, because not every tissue is equally dangerous to receive radiation on. So this is the one we actually measure the radiation damage. It's the effective dose. So we have the doses equivalent, the equivalent dose, and we have the effective dose. And the effective dose, another formula that you don't know everything of. H is this effective dose. E is the equivalent dose of the previous page, which we just turned back a bit. What is WW? Still the unit of measurement is the secret, by the way. WW is the tissue weight coefficient. The tissue weight coefficient. Oh dear. So how much worse is it to get radiation on the one tissue in your body compared to the other? Well, your reproductive organs are the worst ones. And quite surprisingly, your brain is the least dangerous. How is that? What's behind this? Well, that's the natural rate of cell division in a certain tissue. If it goes slow, the danger of getting cancer from that in that tissue is much less than if it's a rapidly dividing one. So that's why the brain, which is the slowest dividing tissue in your body, has the lowest tissue weight coefficient. While the reproductive organs, they divide the quickest, and that's the most dangerous. So shown here is the top 3 of tissue weight coefficients and the bottom one. And look at the number 3 in this list. And where do you receive the radiation from tobacco smoke? Right in your lungs. Ha ha ha. So you have alpha smoke, alpha radiation, the worst kind of radiation, in the number 3 tissue. Oops. Don't do it. Well, H is the base for all radiation protective norms. Limits that we have chosen for which we can accept danger and what is not an acceptable risk. Well, year-based radiation protective norms. Radiologists, people that work professionally with radioactive radiation, may receive 20 millisievert every year. And citizens, people who do not work professionally with radiation, 1 millisievert every year is an acceptable risk. That is what you may receive more than the background radiation. And for comparison, the background radiation itself is 2 millisievert per year. So you may receive, as a citizen, half of the background radiation more than the background radiation. What is comparison? Well, X-ray photo is between 0.02 and 0.1 millisievert for every photo, depending on where the photo is taken. Have you from your teeth, then it's an 0.2, but of your thorax, that's an 0.1. The more body it has to go through, the higher the dose. One you might not expect there. Flying in an airplane. 1 hour flight is about 0.4 microsievert of dose, radioactive dose. Why is that? Well, think about the sources of background radiation, and the number 1 on that list was the cosmos, cosmic radiation. And if you're in the air, you have less atmosphere above your head. And the atmosphere is a very good shield for cosmic radiation. And it's not shielding it anymore. So, flying in an airplane will give you radioactive radiation. A radiation dose. And for your information, having a winter sport vacation also gives you a radiation dose. And we already mentioned smoking. Well, that's a batty one. 10.3 microsieverts per cigarette. So if you smoke 100 cigarettes, you're already above the year dose. And take on average, an average smoker of 1 package per day will receive 60 millisieverts of alpha radiation in the lungs. Well, good luck with that. So keep on smoking if you want to die. Don't do it. Still, for comparisons, what about the direct effects? How much do you need to get to that? We already mentioned you need to get a lot for that. Well, red skin, starting from 0.5 sievert, so a whole sievert, and 1 millisievert per year is your year dose. So 500 times your maximum year dose in less than 1 day will give you a red skin. Ooh. So that's why we don't really are very scared of the direct effects. How about initial radiation disease? Well, then you need a whole sievert before the itching begins. About severe radiation disease, that's from about 2 sieverts. And the last one, death, that's from about 5 sieverts. Radiation of more than 5 sievert is very hard to survive. Actually, not. So don't go swimming in nuclear power plants or try heading back nuclear bombs. That's not very good for your health. It's the last thing you might ever do. So now, how to answer the question we started with. Why did that disaster in Chernobyl take that many lives? How much did for instance, the people who were working in the plant at the time of the explosion, how much did they get? Well, that was about 25 sievert. Oops. So now you know why you have to be careful with radioactive radiation.